Okay, you have looked at horizontal launching, general projectile comprehension, so let's go ahead and add an angle launch. So we're going to go up and back down, but we want to have our reference so the most things are positive that we can handle. So we want to have to the right is positive and up is positive. But where are we going to put our point of origin? I like to put it right here, so on the very bottom of the cliff. So right is positive and up is positive. So my initial position might be up high. Okay. And then my ground doesn't have to be negative. So ground would end up being equal to 0. Don't have to, but this is just one way to do it. But I would definitely have up and to the right is positive. You can go ahead and move your frame of reference wherever you want. You could have it up here. You could have it here if you want to, but that would be too weird. I'd even have it down below and or up top. Now, with these, what is going to be different for horizontal launches and vertical launches? First things first, since I put up as being positive, I will want to have my acceleration due to gravity is going to be going downward. So I'm going to be subtracting that last term because that last term is going to be pulling me down, not up. Now I don't need to change any of the signs on the other. So gravity is acting downward and downward is negative. Okay, so all of those have been changed. Let's go ahead and take a look at the general concepts. Instead of horizontal, we're going to have angle launch. Horizontal velocity is constant. Yes, that doesn't make any difference. It's still going through the air, assuming no air resistance. We can even add that. Assume no air resistance. Gravity still accelerates the object downward. Have your reference frame start at the initial position, but on the ground. And go up. Find the time it takes the object to go in the air. Yes, we will want to do that, but instead of using this equation, we're going to have to come up with something because there is an initial velocity here. Still, horizontal velocity remains the same. So this equation is going to be a little bit harder to do with the y direction, so let's take a look. So with this case, we have our initial velocity in the y direction is going to be h. Our final velocity, or initial position in the y direction is h, and our final position is 0. Now, what's our initial velocity in the y direction? And what's our initial velocity in the x direction? We'll have to figure those out. Okay, let's put those aside for just a second. Anything else that we need to look at? Final velocity, that's fine. We still need to figure out this initial velocity in the y direction. Okay, and let's go ahead and change this y. We can change it to height if you want to. Okay, so looks like there's a couple things we need to do with angle launches that we didn't do to the other. So after you set up your reference frame, we are going to break the initial velocity into x and y components. Okay? And how do we do that? Well, let's take a look at a picture. If we have an initial, let's start red, initial velocity in the y, just at an angle, we could break it up into initial velocity in the x, initial velocity in the y. We could go back to geometry class, and we know that the sine of the angle is equal to velocity in y over the hypotenuse, and we could do the cosine is the velocity in the x direction over the initial velocity kind of hypotenuse. But do we want to do that every time? Because every time we solve for the y component, we always just use the sine, and we solve for the x component, and we use the cosine. So I'm okay with you just going ahead and stating this. You don't have to show the geometry components to it. As long as this angle, remember, is from the x-axis. We're okay doing that. So that's typically what you measure from. So we now have ways to write these out. So we're going to add those to our equation. Let's add them down here. Initial velocity in the y direction is v naught sine theta, and initial velocity in the x direction is v naught cosine theta. I don't typically put these then into this equation here. It would just get it messy. So we can erase these arrows because we now have that component. Okay, so everything that I've circled here is all going to be, make sure it's v naught sine theta. And anything over here is all v naught cosine theta. All right. Now uncircle just so it doesn't look so messy. Got it. Okay, so that's one thing. So one thing that's different is the fact that we need to break our initial velocity into its x and y components. That's a key piece in using angle launches. I'm going to write those down. So we have v sub naught, might be able to do this, let's see, and yep, equals v sub naught cosine of theta. Okay, and we also have the same thing, but we have the y. Just to let you know, if you ever want to do equations, you can kind of see how I'm doing those with, they call it latex form. There we go. So that's how you break the initial velocity up into its x and its y components. Now, what about the time? It's a little bit harder because we can't just look at it as it's falling. It goes up and then back down again. So we're going to have to look at finding out how long it's in the air in a little bit more complex manner. That will take another video.